Can someone just unmute and say if you can?
Yes, sir, it is visible.
Okay, perfect. Thank you. Yeah. Okay. Let's get started. Yeah. Right. So something about me, a little about me before we actually start the lecture. So my name is Hiranmay Darshane. I live in Mumbai, Maharashtra. I'm 17 years old. And this is a very small summary or recap of how I got into AI, right? About AI progress in the industry in general and how my personal zeitgeist has changed with it. So between 2017 and 2019, I was a huge gamer, and AlphaGo fascinated me when it came out, and OpenAI 5, the Dota bot that defeated the best pros in Dota. That was very fascinating, right? That was really the inflection point at which a lot of people like me really got interested in AI, right? It became talk. It became the subject of talk in many circles. And so, circa 2021, GPT-3 um, demo started coming out. 2020 was when OpenAI released. Okay, wait. Is there someone unmuted? I should probably pause then. If there's can can you guys mute yourself? Sorry, 1 second. Okay, I can't mute you, but do you mind muting yourself? I think. Yeah. Okay. Perfect. Yeah. No problem. Yeah. So around 2021, GPT-3 came out, the demos started coming in, and language models at that time, before that, between the invention of transformers in 2016 till GPT-3 or so, they were just seen by the general public as some new cool tool that helps you do NLP tasks, right? Natural language processing tasks. No one really thought of large language models as like a sure shot path to AGI like we do today, right? DALI also came around during that time. It seemed cool. 2022 was when LLMs burst onto the scene, right? July 2022 or so, second half of 2022, LLM started gaining a lot of attention. And GPT-3 Playground was made available to the general public around then. And right now, I'm fairly convinced that we can achieve AGI in 3-4 years if it doesn't exist already, right? The definitions are very contentious. Everyone has their own definition. The goalposts they keep moving. And so right now my feeling is uh, test time scaling, right? Just thinking more at inference time, exploiting tricks like Monte Carlo research, etc. at inference time, like OpenAI did with Omen, like Google is rumored to do with their newer models. And agency, right? Like agentic applications. I think that might be those are the missing pieces of the puzzle. So that's a little about me. And yeah, let's start. So our topic today is understanding grokking. The original title was Grokking. And so grokking obviously is this phenomena in deep learning that we're excited to learn more about today. But grokking as a word, it was coined by I think a sci-fi writer in the 60s or 80s. And how he meant to coin that word was grokking means to understand something so well that it becomes a part of you. And grokking in deep learning, our subject today, is a fascinating and counterintuitive phenomena at the very heart of the unreasonable effectiveness of deep learning. We'll go into the two adjectives. Why is it fascinating? Why is it counterintuitive? And what even is the unreasonable effectiveness of deep learning? We'll go into that as the talk proceeds. So the talk aims to be semi-technical. We're assuming a fair bit of understanding of model neural nets, right? Interpreting loss curves, the manifold hypothesis, etc., the basics. We're not going to go into details or implementations or technical examples. You might not even see a lot of math, right? We're not going to deal with any of that. But our explanations aim to be technically grounded, and the idea is to help you attain, right, like a good intuitive grasp of things by the end of the lecture. I'll send a separate document with elaborate references, citations, and related links later. And so we'll start with the introduction to grokking, the importance of it, and then some possible mechanisms of how it might happen, right? So some very quick background pertaining to deep learning. Deep learning quickly gained traction, attention, and became the number one approach to designing artificially intelligent systems after AlexNet in 2012, right? Everyone knows that. Um, and a part of what makes deep learning so effective is that deep neural nets learn functions and representations that generalize very well, right? That is something that deep neural nets could do that something that this paradigm of deep learning helped us to do, right? Functions and representations that are learned over time and that are generalizable, that are exploitable to a great degree. So a natural corollary of this fact is that you can train a neural net to perform a task X, right? Whatever task X that you get it to perform using Y amounts of examples, right? Train it on Y amount of data. And then somehow magically, by the virtue of deep learning, your model becomes fairly effective on N examples and inputs, right? On N tasks, N instances of the task X, where N is much greater than Y, right? You're training the model um, on not small amounts of data. It is a large amount of compute and data that goes into the training part. But once that's done, your model does well on a plethora of tasks, right? On a multitude of tasks. So the unreasonable effectiveness of deep learning, this is a phrase that's thrown around a lot in academic circles when talking about deep learning. And so there's this thing called the manifold hypothesis. So manifold, if you don't know already, you could just assume it as like a multi-dimensional plane. It doesn't matter much, but we'll go about it. We'll go into it now. Many high-dimensional data sets that occur in the real world actually lie along low-dimensional latent manifolds inside the high-dimensional space. So whatever task that you're doing, regardless of how many data points, regardless of how big or how huge the dimensions are, how many dimensions each of your data point has, regardless of that, the useful stuff, what you're really looking for, the patterns that you're really searching for, they lie in fairly low dimensional space. That's the manifold hypothesis. And experimentally, one second, can you guys mute yourself? Uh, Please mute yourself. One second. Uh, Mute. I can't mute. Okay. Please mute yourself though. Yeah. Um, how do I mute people? Mute. Okay. Okay. Right. Um, One second. Right. And so the manifold hypothesis, we went over that and it has held true so far, right? Experimentally. And the challenge really lies in finding these small number of variables that we talked about in the manifold hypothesis, or this latent optima or latent information, right? This idea that what you're really looking for, the patterns that you're really looking for, they're fairly low dimensional compared to just how dimensional your data points are. And deep learning does seem to do so very well, right? It goes about identifying these patterns, albeit unscrutable, right? You can't really go and look into what those patterns that are being learned really are, but it does that very well and exploits this fact to do very well on tasks. And so there's a claim or thesis that got floated around in 2022, just before neural nets, just before the LLMs really took off, which was that neural nets are simple curve fitters that memorize things. And this claim was echoed by this very famous phrase called LLMs are mere stochastic parrots, right? A parrot who just, you say X, he says X, you say two, he says two, right? And this was a claim that got floated around that time, which really follows to this, which is a great example of this thesis that many people hold, that all that the neural nets are doing is simple curve fitting. But but how do you explain this, right? So here's GPT-4o, and I asked it to write a Shakespearean sonnet about grokking in deep learning. Sorry, about grokking in deep learning. And so clearly the model didn't see this in its training data set, right? Clearly it did not, right? This prompt obviously did not appear in its training data set. And so it is generalizing out of distribution, right? The distribution that it was trained on, it seems to excel at a task. It seems to excel at doing a task which is not within that distribution. And so this out of distribution generalization clearly and evidently disproves that hypothesis of stochastic parrots. And so this relates with grokking because generalization is grokking, as we'll see more in the next slides. So could your neural net do that, right? Writing a Shakespearean sonnet on grokking and deep learning, could it do that just by memorizing and reproducing things it saw in the web text training data set? I don't think so, right? It clearly needs something more special. It clearly needs something more profound to do that, right? Just a second. Yeah, okay, right. And so here's the slide here's a chart that I think best represents grokking, right? This is a chart from a research team at Google. And so a very basic loss curve that we'll interpret right now, right? So there's accuracy plotted against training step or time or compute, however you want to think about it. You could think of training step within many different proxies, but the model quickly fits the training data with 100% accuracy, right? Whatever it was shown, whatever distribution it was given to be trained on, it perfects that distribution. It understands that distribution very well, right? 100% accuracy. But on the test data set, right? These are tasks that are similar to the tasks in the training data set, but they are slightly different, right? Maybe think of different numbers or just different tasks, but they're following the same nature of task broadly, right? Different examples, different instances of the same task. And it doesn't do better than random guessing on the test data, right? It's you train the model, train the model, train the model. It's not doing something. And at some point, the accuracy on test data really improves, right? At this point, your model, which was not doing well, um, on examples that it had not seen in the training step. It wasn't doing well on them, and then suddenly it does very well on them, right? It generalizes, so as to say, and there's a delay, right? You can see that there's a delay, um, and so Grokking was the name given to this phenomena, but something along in the vein of grokking, right? Something similar to grokking without actually without actually having the name grokking existed for a long time. Many similar examples. So here's one that's called deep double descent. I think this phenomena was observed by a team at OpenAI 3 or 4 years before grokking, right? So again, very similar thought that the model quickly does very well on the training data set, right? The error is asymptoting towards zero. And then as you uh, as you increase the complexity meaning as you train the model more, it's not doing well on test data, right? And so in some sense, it is overfitting on the training data, right? It is overfitting on it. And so that means that performance on test data, theoretically, going by whatever knowledge exists in statistics or learning theory, going by that knowledge, uh, the, the the error on test data should increase, and it does increase. But at some point, it suddenly falls, right? The model starts doing very well on examples that it hasn't seen. Um, Deep double descent was the name given to this phenomena, very similar to grokking. So, general outline and explanation of what's going on. Sufficiently parameterized neural nets can quickly overfit training data, right? Whatever you train them on, they learn to do very well on those tasks very quickly, given that, yeah, provided that your model has enough parameters. And the model does so as it develops mechanisms or circuits to produce the right output that corresponds to a task. We'll go into what a circuit is later. And in some sense, it memorizes the corresponding outputs to a given input, or it provisions for these input output pairs on a case to case basis, right? And so, given enough time and compute, you train the model for longer. The model finds a way to generalize on that task, right? It sees some patterns, it just gets it. And so, in that sense, it isn't simply producing the answer. It's not just simply remembering an input output pair, but it is understanding the underlying process that led to that answer. Intuitively, the model, when you train it on, say, f of 2 equals 4, f of 3 equals 6, it's simply remembering f of 2 equals 4. Input is 2, output 4, input 3, output 6. And at some point, it groks, it generalizes. And so instead of simply outputting f of 2 equals 4 and f of 3 equals 6, it gets the fact that f of x equals 2 into x, right? Very, very dumbed down example, right? But it's a good illustration of what's happening in the grokking. You're not just learning to memorize the input and the corresponding output, but are somehow understanding the process that went into it. So main motivations to understand grokking. Why do we want to understand it anyway? What makes it so interesting and important? So grokking correlates with generalization, and we discussed a fair bunch about generalization, right? How important that is for neural nets. And so much of the effectiveness of modern neural nets comes from the ability to generalize outside the distribution. And so emergent abilities, as they are called in the newer language models, right? Post GPT-3 language models, many papers have been written on these emergent abilities. And so emergent abilities are perhaps a special case of grokking and generalization, where these abilities emerge, right? When the model somehow builds these abilities as part of the training phase, as part of an objective that is, hey, you should do well on the data. You should get good at doing the task, whether it's predicting, classification, whatever. And so secondly, grokking is a huge violation and exception to our existing knowledge, right? As we saw in that deep double descent chart, where the model is when the model overfits on training data, and it's expected to do increasingly worse on the test data, on data that it hasn't seen because it has already overfitted. That does not happen, and suddenly the model generalizes there as well. And so grokking challenges our traditional assumptions about neural network and how about neural networks and their training with unexpected phase transitions, right? Grokking is, in some sense, you could think of it as a phase transition, right? Thirdly, it raises foundational questions about learning. That delay that I pointed out between just overfitting on training data and starting to do well, starting to generalize on the testing data, it does raise a lot of foundational questions about learning, right? Why does prolonged training, why does it happen so that if you train the model more and more, you end up with a model that has generalized instead of overfitting, right? Why does that happen? What does this tell us about the nature of understanding something, right? In context of neural nets. So our broader objectives for today, we will try to understand and answer the following question. Why is grokking possible at all, right? Is there a theoretical guarantee that a neural net will develop a generalized understanding of a task? Are there any prerequisites for that? Second question, why the delay? Why that gap? This is very paradoxical. And so why does this paradoxical phenomena of generalizing or grokking when the model has overfit and is expected to overfit even further happen, right? Why does the model suddenly generalize? And so how, and the thirdly, how does grokking happen, right? How do you feel it? How do you imagine it mechanistically? What's a good intuition for that? So let's take a step back here. Let's, kind of go back to the fundamentals of training a neural net. And so imagine that in the process of optimizing cost or loss, a model through backpropagation, through stochastic gradient descent, and through other optimization techniques, it develops an ordered set of weights and activations, and we'll call these circuits. We'll give you more intuition about that, but for now, let's call us these circuits. Broadly, we want to think of the model achieving a general goal X via some internal algorithm or mechanism that we will call circuits, right? So let's say you could say a model has developed a certain circuit that does task X, right? And so now it's important to note that a sufficiently large neural net can learn or approximate pretty much any such well-defined mechanism with some caveats. This is the universal function approximation theorem. And so we'll take the idea of thinking in terms of circuits further. It's useful to think, it's useful to loosely think of circuits as mechanisms that try to approximate and model a given loss landscape or curve. So mechanistically, when you really think about it, within the model, there seems to be some pressure or optimization that favors generalization, right? Why does that happen? Because there's obviously something that is some pressure that gets the model to generalize, that causes this phase change. And so let's formalize pre-grokking circuits, right? So the model is doing task X using, and it hasn't grokked on the task X, right? It's doing well on the training data, not so well on the test data. And so there's this pre-grokking circuit which memorizes the task. Let let us call that circuit the circuit mem, right? C dot mem. And sorry, and let another circuit called circuit gen, sorry for the typo, let another circuit generalization denote the set of weights or circuits post grokking when the model has actually started to generalize, when the model is doing well on the testing data as well. Right, one second. Right, okay. So before we really go into the possible explanations, I want to give you like a very high level overview. It's a list. We'll go through that list very quickly. We'll take our own time. We'll take a fair bit of time to go through each one of them one by one, but quick list to speed through right now. So sheer scale of neural nets, there's this hypothesis that if your neural net is big enough, if your neural net has enough compute, enough parameters, it will grok, right? The intuition here is that a bigger neural net gives you more possible circuits, right? Right. You take more parameters, you take more activations, you take more edges in your neural net, and that obviously increase the possibility of finding that one circuit that generalizes, right? Combinatorics, so the total possible combinations exponentially increase, and the possibility of you finding that one circuit that generalizes well increases as well. Analogies from physics. There's a thing called the least action principle, which says anything that does less, a path that does less, or a mechanism that does less is favored. Brownian motion, random walks, mess around and find out. We'll go into that later. And there are some topological considerations that follow from the loss landscape of neural nets, right? When you really think of a model in terms of a mechanism that is trying to achieve the global local the global sorry the global minimum point, right? Or a mechanism that's trying to achieve the global optima, right? um, so topological considerations will go into those. So deeper, wider minimas are better than sharper, shallower minimas, right? We'll go into that. So the intuition here is that deeper, wider minimas are very specific, non-generalized memorization um, type points in your loss landscape. Um, and we really want to find these stable, deeper, and wider minimas, right? Like you can almost think of them as a basin in the loss landscape, and we favor those. So the intuition here is sharper minimas mean memorization. That implies non-general solutions, and wider basins implies generalized and widely applicable solutions. We'll go into that intuition later. And so there are some perspectives or analogies from information theory that imply that a shorter method to do things is favored because it generalizes well. We'll go into that as well. So um, another really important element of grokking is human engineered penalties and regularization techniques, right? These are things that are engineered into the model, engineered into the optimizer and the general training process by humans and by engineers, right? So there's the L2 regularization or weight decay, which penalizes bigger weights and encourages smaller ones. The intuition here is larger weights imply more information, imply more specification, right? And that in some sense relates to memorization, right? You're trying to learn, you're trying to remember more, you're trying to learn very specific things of the data. And sparsity is another regularization technique. It's a penalty that's applied. And so what sparsity does, it uh, in your neural net of all the weights that are smaller than a certain threshold, we will round that down to zero. And the intuition here is that memorization means treating things on a case-to-case basis, literally, right? You're treating everything on a case-to-case basis, memorizing each one of these, not having a general pattern that you can exploit, which means that you have a lot of ad hoc weights, right? A lot of specific weights. In some sense, memorization things would require you to have more weights. It would require you to have more specific hypotheses of your environments. And generalization would not. It would scale very well. So let's look at each possible explanation one by one. And there's a spoiler alert. Neither of them is singularly and exclusively responsible for grokking. All of them interface together. Each of them is required. Spoiler. So the first perspective, that scale and combinatorialness equals grokking, right? Extremely deep and large neural nets imply grokking. Is that true? Um, so going back to our circuit that memorizes versus circuit that generalizes approach, it's tempting to think that a larger neural net simply allows for more combinations of circuits, right? More weights, more nodes, more edges. You have a bigger graph if you think of a neural net as one. which means the combinations just increase exponentially, right? And a smaller neural net simply does not give you enough degrees of freedom, right? It simply does not give you it simply does not give you enough of total possible combinations to best approximate the curve or the loss landscape that you're trying to model, the curves that you're trying to model. Apologies. So simple example, a cubic equation gives you more freedom to model a given curve than a quadratic one, right? An equation of an equation of the third degree, you can use it to model some random points lying on the plane. You can use that third degree equation to model those points much better than you can use a 2 degree or 1 degree equation, right? More degrees of freedoms are always more useful. So this argument is best represented by the lottery ticket hypothesis. Uh, the lottery ticket hypothesis, the word comes from a paper from a few years ago, and it states that the dense network contains a pool of subnetworks. If you go back to thinking of neural nets as a graph, as a network, it has a so
Thani slip.
you 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 want to choose, you want
Lura.
to have a very specific
Ah,
subnetwork, and out of all those total subnetworks,
ah,
only a subset are winning tickets, right? Those are what you are really looking for. And if you have more total subnetworks, it's clear that your probability of finding that exact subnetwork that helps you generalize increases. And so the authors of the paper state, we extend our hypothesis into an untested conjecture that stochastic gradient descent seeks out and trains a subset of well initialized weights. Dense randomly initialized networks are easier to train than the sparse networks. And this is because there are more possible subnetworks, as I said, from which training might recover a winning ticket, right? The subnetwork that you're really looking for, a circuit or a subnetwork that generalizes really well. So the core hypothesis here, to summarize what you said, sorry. Yeah. So the core hypothesis here is, again, you have some small subnetworks that give you multifold performance gains, and a bigger network just allows you to increase the probability of finding those. Some further intuition for scaling and grokking. Any problem X can be broken down as set of tasks that in theory are representable by nonlinear functions, right? By very well formalized functions, by very well representable functions. And so the universal function approximation theorem implies that such functions can be approximated arbitrarily well by neural nets with a finite amount of weights, right? With a sufficient amount of weights. And bigger neural nets just give us more parameters or weights, going back to that word, degrees of freedom, total combinations to represent things. Something about the topological considerations of the loss landscape. So this is a little tricky to go about. Um, so on the z-axis, you actually see loss, right? And you want to minimize loss. So in some sense, you want to find the point that lies at the lowest altitude, right? You want to find the bottom of the pit, literally. And so on the x and y axes, there are any two random weights that you can plot. And so what we're really looking for is is a point in your manifold that is wide, that is wide and deep, so as to minimize the loss, but it has to be wide. And I'll give you some quick intuition about that. And I think maybe we can return back to this figure once that
ah.
is built. Maybe we can return later to this figure again. So the loss landscape that I just showed you plots the loss function on the z-axis against parameters or weights, say wx or wy on the x and y axes. And there lies a certain combination of weights that makes it so that the loss landscape has very deep and wide minimas or basins. Graphically, this means graphically a good way to think about it, a good way to imagine it, is that some random change in the wx or wy, uh, even given that change, the loss function remains below a certain minimum. And this means the model has found a very robust and general solution, very robust and general um, set of weights a very general state of the model that is not sensitive to small changes in weights, right? And so, uh, one second, maybe it's a good idea to go back to that figure. Right, so of all the parameters of the million, billion, and nowadays soon maybe the trillions of parameters that a model has, you plot any two of those, right, the ones that actually matter, and there lie regions in your graph which keep the loss function below a certain minimum, even if you change uh, parameters a little. And this goes back to our regularization intuition. If you think about it, our regularization intuition, if you remember it, was that we want we want a set of weights. The intuition was that just more specific weights mean that you are memorizing things. And so if you are memorizing things, if the model is memorizing things, a small change in the weight, a small change in the parameter might ruin the model's chance of succeeding at the task, thereby increasing the loss, right? And so a very low lying solution just means that that solution uh, that set of weights, it's immune to those small changes in other weights, which means you are not memorizing if you go back to that intuition. So stochastic gradient descent is best imagined as a ball dropped from the peak of the loss landscape and getting drawn into minimas and basins, right? That is what the optimizer does. We are trying to reduce the loss, right? We want to find the bottom of the pit, as I said. Now take this further, and instead of just gravity as the pressurizing mechanism, instead, if you think of the optimizer optimizing for more than just the loss function, imagine another optimization penalty, that is deeper minimas, deeper and wider minimas exert another force that draw the ball towards wider basins, right? Towards that set of weights that is robust to small changes, that is not memorizing, as I said. And so with enough parameters, your loss landscape is continuous and well formed. SGD first hits very spiky and sharp minimas, which are non-general solutions. Memorization, right? Those that in that state, the model is memorizing things. And because our model has a very nice continuous manifold, there are these wide basins, and stochastic gradient descent, when given enough time, will perform a random walk, much akin to Brownian motion, right? What a gas molecule does in a heated chamber. And so there are these guiding pressures that not only optimize its loss function, but also take it towards regions or areas in the loss landscape that are robust to small changes, that are not memorizing, so as to say. And so that exerting force is, perhaps you could think of that as something that's hard coded into Adam W and such like SGD optimizers. They have hyperparameters, so to say, that do that. And so here's a nice paragraph from a researcher at Google. I think his name is Perrin, and he says, to sum up, why does deep learning even work? Due to extremely high dimensionality, almost all critical points away from the optimum are saddle points which can be escaped easily, right? Your optimizer can get away from that rut. And so when SGD finds the basin near a global optimum, it is exponentially more likely to find a basin with lower curvature and hence vastly greater volume, right? Exactly those regions that generalize, that are not prone to small changes in the weights of the model. And so even if SGD does not find the largest, flattest basin, given isotropic dataset noise, isotropic here just meaning that every direction of your loss landscape is similar, so as to say, right? Regardless of what direction your optimizer chooses to take, it's going to have a similar time dealing with all of it. And so SGD in such a case is guaranteed to perform a random walk, right? It's trying out things. It is trying out uh, one set of model weights, another set of model weights, and it's going to settle on the one that reaches that wide minima, as we said. And this explains results like Grokking, right? When given enough time, stochastic gradient descent won't just achieve an optima that is sharp or memorizing things, but given enough time, it will reach those flatter, wider, deeper basins, so to say, that generalize very well. In short, this is Beren's intuition for what grokking is, which will summarize all our discussions very well. A sufficiently over-parameterized neural network possesses a coherent and spatially contiguous optimal manifold, as we talked about in the previous slides. And so SGD first falls towards and hits the manifold. And once it is on the optimal manifold, it performs a diffusive random walk, right? Brownian motion, so to say. And the optimal manifold contains regions of greater or lesser generalization performance, with most regions representing useless overfitting, right? Most regions are just examples of a very specific, very finely tuned set of model weights that memorize things, right? And so, but some regions exist in your landscape where where the parameter space matches the true function in some sense, where the network can obtain high generalization performance, those deeper minimas. And ran long enough, SGD will eventually drift into those generalizing regions. A lot of it has to do with hyperparameters of your optimizer and such like things, as in how does your optimizer interact with the loss landscape, right? How does it decide how to increase the momentum, how to take bigger steps across the landscape, how to go about and have more accurate updates? How does it decide to do all of that? And so we've taken a look at the scaling hypotheses. We've taken a look at explanations that follow from topology and such like domains. Now we want to have some alternative perspectives, some eclectic connections and analogies from physics and compression. Here's a nice meme. I use alternative to medicine, same thing, but it's not alternative if it works, right? It is definitely out of domain. It comes from physics. These analogies come from physics and compression theory, information theory, such like domains. But if they work, they're not alternatives. Let's see. That's up to you to decide. And so we will start with some connections from physics and compression. First one is Occam's razor. And so Occam's razor, if you might have heard about it, which basically goes, um, the best explanation is the one that assumes the least number of things about the environment, right? Assumes less equals does better when trying to explain something. The original some backstory, some lore. It doesn't matter here. But this Occam's razor thing was put forth by, I believe, a king in medieval England whose name was George Occam. So it was Occam, and it turned to Occam. Whatever, it does not matter. So his original sentence was in Latin, and that translated to English is verbatim translation is: entities should not be multiplied beyond necessity. You should not have more assumptions when you can get by with a less number of them. A theory with fewer assumptions is more likely to be correct than one with many assumptions, provided both explain the same phenomena, provided both are doing the same thing. Another connection, this comes from compression theory, from information theory. This is called minimum description length. This is a general principle that advocates for methods that aim to keep the descriptions and representations as simple as possible by minimizing the information or length or cost needed to describe them. And essentially, this promotes better generalization and prevents overfitting, right? It relates to Occam's razor in some sense. So connections from physics and compression, we've put forth these two analogies, namely Occam's razor and oh, sorry, can you guys mute us 1 second? Sorry, 1 second. Yeah, nice meme. Thank you. Thank you. Yeah, nice meme. Glad someone saw that. Yeah, I'll take your question later. Sorry. Yeah, let's proceed. Sorry for the interruption. Yeah. And so we did look at those connections, namely Occam's razor and minimum description length, but we really want to identify what's going on, right? What is the intuition for why shorter explanations that assume less things? Why are these better? So here's a very there are no equations, as I said, starting out, but okay, let's see. Shorter and more direct representations assume less about the task, which means there is no ad hoc provisioning, right? There is no provisioning for for an input output pair on a case to case basis, right? When you have more direct representations, it just means that you're not assuming that it just means that you're not assuming things. And when do you assume things? When you're trying to explain phenomena on a case to case basis, right? And so simple deep learning circuits act on some biases, right? They take in inputs, they observe some part of those inputs, and then uh, those are the biases that they act upon. And these are general assumptions about the nature of data, right? It depends on your inputs. And so more biases mean that you're assuming more things. If I'm taking in input and I'm trying to look at 100 different things about the input, whether that's a text classification thing or whether that's an image generation thing, if the model is looking at so many of these things, if there are so many of these biases, it means that it is provisioning for things on a case-to-case basis. It means that is only applicable for very finely tuned or precise occurrences of data. Some more intuition. Um, you have an input-output pair, and your task is taking the input and predicting the output. So now you could go about this by just seeing things in the input and uh, trying to grok a general pattern, and then depending on that you proceed towards the output, right? More biases just means that you're looking at very specific, very detailed things, right? If you have data points of 100 dimensions, and of the 100 dimensions, if you need to look at 100 of them, and for each case you are looking at very finely tuned magnitudes of of each dimension, hopefully that makes sense. It means that it means that you're provisioning for things on a case to case basis, and you're not generalizing these things that you are capturing, these things that are capturing across so many dimensions. You're taking a look at so many dimensions, not able to find a certain pattern. These are noise. These things, these small changes that you're sensitive to, that act as your biases, these things are noise, not patterns, right? These are noise. Some fine changes across a certain dimension of a common data class isn't a pattern, it's random noise. If it was a pattern, it wouldn't change finely, it would be fairly consistent. And because there's a data class of consistent things and only a few things change each instance of it, it has to be noise, right? Otherwise there's no general pattern, uh, otherwise there's no consistent data class. If you're remembering these things, that's noise. You're not finding the general pattern, your model is not doing that, and the model is doomed to fail if the noise is what it pays attention to, right? The noise, if it pays attention to that, it's doomed to fail because it straight away means it's memorizing things on a case to case basis. So to summarize, we'll try to compress all of our talk about these things into a small paragraph. We'll try to summarize that. Longer description length, right? Which in our field, which in deep learning relate to bigger and more weights. This implies ad hoc provisions on a case-to-case basis, only applicable in very few cases. And this implies there is no generalization. So if you try to take the converse of this statement, and by contradiction, if you try to prove this by contradiction, you need shorter description lengths to generalize. Hopefully that's a nice way to look at things, right? If longer description lengths imply memorization, if you take a very if you take a very straight converse, negation, inverse, whatever of it, you end up at a proof by contradiction that the shorter description length generalizes best. Here's a nice slide from Ilya Sutskever from the year 2018. Um, and so I think we it the points there are slightly redundant in the sense that we've talked about those already, but it's a nice summarizing paragraph anyway. So the idea is that uh, all conceivable regularity, all conceivable patterns are expressible as a short program, right? Going back to our intuition, and so no short program meaning it implies that it implies that you're paying attention to totally random noise. It implies that your program is very large. It's taking 100 different things into consideration, and it's paying attention to noise. It's not paying attention to any useful pattern lying underneath. And so another connection from physics is the least action principle. We will go through this part very quickly, very fast. And so the least action principle loosely states that an object follows that objects follow trajectories that minimize action, which is a physical term that takes into consideration length, time, etc. And in our case, action is best thought of as just the specificness of weights, right? How many weights do you have, and how finely tuned do you need those weights to be if you want to succeed on the task, right? If you need that to be of a very high magnitude, you are memorizing things. The model is memorizing things. The model is not generalizing. Um, and so it you could also look at it in a sense that how many different circuits do you maintain, right? Least action principle could also imply that less number of circuits, yeah, that is the optimal way to go. And so the LAP here loosely leads to an intuition that the circuits with maximum generalization and minimum action win. And so compression theory, so the Kolmogorov complexity, you could think of it as just a very complicated term to describe the minimum description length that we went across some slides ago. And so there's this very new paper, it was in peer review a few days ago, and I think the authors publicly unveiled it just yesterday. I will update it later. It states that we study the complexity dynamics of neural networks to explain Grokking. And to this end, we introduce a new measure of intrinsic complexity within neural nets based on the theory of Kolmogorov complexity, which loosely relates to minimum description length, right? How less or how high or how highly specific your weights or your model really is, right? Minimum description length, Kolmogorov complexity. They measure it by using some proxy metric that is readily observable within neural nets, and they track that proxy metric throughout the neural network, throughout the neural network's training process. Sorry, and they find a consistent pattern that complexity first rises and then it falls. And if you think of it, you could loosely think of it, you could loosely um, have this realization that complexity rises in the sense that the model is memorizing things in the very first slides of our graph. It's memorizing things. It's doing a lot of specific maneuvers, very specific uh, tuning of weights. Complexity rises because it's memorizing things, and suddenly the complexity falls. Suddenly it is finding shorter, better ways of describing things. And so so we have proof that minimum description length, Kolmogorov complexity, and all these analogies actually play in, and that they actually uh, play well with theories of Grokking, right? A very nice paper, very nice and recent paper. So empirical evidences of human engineered factors that lead to Grokking. We did go over sparsity and L2 regularization and such like things. And so L2 regularization, which isn't weight decay, but you could think of them as one thing in this paragraph, in this context. The key insight is that when there are multiple circuits that achieve strong training performance, weight decay, in the sense that weight decay is just regularization. You want to make the weights of smaller magnitudes, and the ones that are of very small magnitudes want to squish them to zero. So the insight here is that weight decay prefers circuits with high efficiency, that is circuits that require less parameter norm, less, again, just to produce a given logic value, as in to arrive at the same output. So, okay, all this is fine. We might or might not have a good enough intuition of how grokking happens, why grokking happens. But what explains the delay, right? We did use the word fascinating and counterintuitive. Fascinating, it is still fascinating, and we might have demystified it to some degree, I hope so. But what explains the counterintuitiveness, right? It is still counterintuitive in the sense that there's this big delay, and this delay you could try to think of in terms of SGD is just doing Brownian motion over the loss landscape, and it takes its fair bit of time to arrive to the right solution, right? It takes time. But is there a more elegant way to look at these things? Yes, there is. So here's an excerpt from a book that was written in the field of neuroscience. And this book was, the author wrote this in 1998. And so the excerpt goes, to learn a first symbolic relationship requires holding a lot of associations in mind at once, while at the same time mentally sampling the potential combinatorial patterns hidden in their higher order relationship. You could think of this as what SGD does, right? You start off with an initial hypothesis, and you want to explore the search space till you achieve a better more optimal solution. And so even with a very small set of symbols, the number of possible combinations is immense, of course. And so sorting out which combinations work and which don't requires sampling and remembering a large number of possibilities. Very fascinating that the author came loosely described what is uh, loosely described how we look at grokking today. This was a book written, as I said, in neuroscience, on the topic of how people learn, how people, uh, how people situate things, and topics within abstractions and such like things. And so from the same blog, this quote is via a person called Dwarkesh Patel. He has a great Substack, great blog on AI, deep learning, such like things. I would highly recommend you to go and check that out. From the same blog, Dwarkesh Patel has another very insightful comment. The previous paragraph explains why the model needs to be over parameterized, right? It needs to have this search space that is sufficiently large for it to really poke into and find out the optimas. And you need space to store the memorization circuits, right? You need space to store these memorization circuits, these sub networks, these lot. And sorry, this is the memorization circuit, not the generalization one. Sorry. So you need space to store the memorization circuit, in the sense that you start off with an initial hypothesis that you improve upon and then later achieve clocking. And this space to store the memorization circuits, which are basically just storing all the input output labels in the pattern in the training data, right? Not looking at patterns, just memorizing input outputs. And you need extra space to do the combinatorial search to find the generalized solution, right? If SGD thought experiment, if SGD abandons the idea of memorization altogether and starts off trying to go about the search space very randomly, trying to find a lottery ticket, trying to find that generalizing circuit, that is not a very optimal thing to do, right? Uh, in some sense, you could relate this with the Bayes theorem, right? Which states that your posterior probability, right, your new information is in some sense very highly affected by your priors about what you know today. You get new information, you update your priors, and then you end up with the posteriors, right? Um, and so if you take a look at this if you take a look at this from a very Bayesian point of view, you could think that you need to have a very nice minimum viable prior at the beginning, which is memorization, and you need that good prior to take in new information and then develop a fair understanding later, which is grokking, right? And so this means you need some space to store that, right? So over parameterization does that and allows the model to explore a much richer hypothesis space and to try out different potential general solutions. This means that the model can represent more complex functions and paradoxically find simpler or more generalizable solutions within the larger space. Right. So it takes time. And this also explains the inconsistency that I showed you in the deep double descent graph, right? Um, the testing error is supposed to shoot up, but it does not. But it takes time for it to actually go down. And this paragraph, I think, beautifully explains that paradox, right? Um, that to find simpler or more generalizable solutions, yeah, you need to do that. So we've covered a fair bit of ground so far. We've looked at different perspectives. And so what ties all of this together, right? Is there one single thing that explains grokking and altogether, right? Can the Jenga-like tower of grokking, right, if you look at grokking, it can be explained by multiple different things that happen at multiple different stacks of the entire end-to-end training process. And so can this tower still stand if you remove one random piece? Probably not. Probably not. So to summarize and tie things up, to explain um, just how across the stack these things is spread, to explain that and to summarize things, The sheer scale and combinatorialness of deep neural nets allows for this lottery ticket like hypothesis, right? Like that you find subnetworks that generalize very well. You need scale for that, as we've explored in the previous slides. The topological considerations are all very important, right? The way SGD goes about uh, exploring the loss landscape is very important, which uh, later leads to grokking. Information theory, compression, physics, etc. All these analogies from such subjects give us very elegant proofs and intuitions about a lot of phenomena associated with grokking, and the importance of human engineered factors like weight decay, L2 regularization, gradient smoothing, which is a hyperparameter in the optimizer. The importance of these factors that we engineer into the model, right? Hoping for grokking, these can't be overstated either. So what would have happened if Adam W or the optimizer had fundamentally different biases, right? Momentum correction or how it goes about the loss landscape. If these were wildly different, what would happen? If would we still have grokking? What would have happened if we hadn't cracked large scale distributed training and optimization? You need to have scale to achieve grokking. You need to have large neural nets when you're trying to grok across different tasks. And for that, you need to figure out how to run these training algorithms on so many different clusters. And so these are just two parts of the stack, right? The uh, the cluster part, the distributed systems part, and the optimizer parts. Of all the other parts in the stack of the end-to-end training processes, there are multiple such what would happen if, right? If, buts, and maybes. So many of those, etc. So many of those, right? And so things are nuanced and complicated. And with all complex systems like neural nets, outlier phenomena, like grokking that really surprise you, that really throw you off, right? What's happening here can only be explained in retrospect. In the entirety of things as a whole is more valuable than the parts summed up alone type of way, right? There's a word for this. There's a German word for this German concept in philosophy that's called Gestalt, right? The idea that when things together, the entire stack of end-to-end training stands together, it is much more valuable. And throughout the internal interactions, it does things that couldn't have happened if you just take things out, etc., etc. Right. And so there's a good chance. Sorry, is this a repeated slide? No, sorry. So, okay. So there's a good chance that grokking wouldn't have happened, and neural nets wouldn't be half as useful today if a few things across the stack differed even very slightly, right? And so nobody really understands what's going on, right? This is a very experimental science which nobody is really used to in the world of computing and physics and the other natural sciences, where everything is operated very deterministically. You have very tractable models that you can poke into and develop rich hypotheses. You don't really have that in neural nets, right? How could you have predicted something like grokking to have happened before even training a neural net, etc., right? We just have no clue what's going to happen and what happens underneath. It's more like alchemy or whatever chemistry was in the Middle Ages, as opposed to better, more richly developed sciences that we have today. You experiment, you have some intuitions about how things work, and some of the intuitions are good, some aren't. This is a quote from Noam Shazir. Um, and so I'd like to end with this great quote from Ilya Sutskever that goes, "Alchemy exists, it just goes under the name of deep learning. You can think of training a neural network as a process of alchemy because we did not build the thing, we built a process that actually builds the thing." And with that, I'd like to thank you. I think it's been a fairly long presentation. I started out with 25, 30 slides. We've reached slide 49. I added 19 more slides later. We've finished at exactly 8:30, 1 hour after we started, or at least 1 hour after we were supposed to start. Again, I'd really like to thank you all for taking the time out and attending this lecture, and I hope it was worth it. I'd be open to any feedback, any questions, any comments, whatever you may have. I'm very excited and eager to hear whatever you have to say. Yeah, if there's anything you want to say, yeah, sure. Yes, yes, Vasu, thank you. Thank you very much, Monica. Thank you. There's a question from Abhishek that I said I'd take later. I think it would really help if you can bring down the language and provide examples which are more level one and level two. Oh, I'm so sorry. I'm so sorry that I did not take our time to really understand that question. I'm so sorry, but as I said, there's a separate document with links with links to blogs and tutorials that go over things. I'll send that link to Sridhar and the Visuara team, who I think the team will relay that link onto you. Yeah, yeah. I think thank you for taking out the time. I can't really share it right now. I'll have to send it to him, and then he will share it with you. That is what was mentioned in the protocol list that they told us. Yeah, yeah. You're welcome. Yeah, yeah, yeah. I think that's it. Again, if there's anything you want to say, will this session be posted in Visual? Yeah, yeah. It will be posted. Yeah, it will be posted. The Visuara team will upload it. I think the AIR meetings and talks, they are posted, I guess, 1 or 2 days after the actual lecture happens. So yeah, I think it will be posted 1 or 2 days later. Yeah, yeah. I think I'll wait for 1 or 2 minutes to see if there's anything you have to say, and then with that, after that, we will end the meeting. Okay, yeah. So I think that's it. The session, as I said, will be posted on the Visuara channel 1 or 2 days later. The session was very informative, but I have a question. Many students asking no technical to get deep learning. Can you just say that? I think this is a question that uh, it's really tough to answer because everyone has their own path. Everyone goes about it in their own way. But a very general approach to it might be it might actually be just play around with the existing AI tools, right? If you can get access to an API, if you have API credits, play around with that. Whatever hyperparameters the API provides you, temperature, top K, etc. Go about manipulating those things. Look at what's happening. Once that's done, once you develop a fair bit of intuition about how these systems work, then it would be nice to directly jump into uh, would be nice to directly jump into papers as opposed to just reading textbooks. It would be great if a person just develops that minimum viable understanding of these systems and then goes about reading papers directly. If papers, meaning those that have been historically important, right? Attention is all you need. Transformers, to give an example, that would be a fairly optimal strategy to learn things. Yeah. And so, to compensate for the lack of technical background, I think a few weeks of training in any language for Python might suffice. Yeah. Is there a good material to learn about continuous manifolds? I think Beren.io, the site that I linked, the blog that I linked before in the slides, Beren.io. I'll spell that out in the chat if you need that. Beren.io. Yeah, so that blog is great. I think you will find material related to manifolds and this general way to look at deep learning as optimizing a loss landscape. There's a good chance you will find something useful there. Thank you. Yeah, yeah. I appreciate that you found the meme funny. I'm happy you found that. I am happy that you found that meme funny. Yeah. Again, if there's anything anyone wants to say, I'm happy to sit back for 1 or 2 more minutes and then we'll end the meeting. Right? We've exceeded the time anyway. Any place from where we can learn about creating AutoGrad from scratch? What's AutoGrad? One second, am I missing out something? One second, one second. AutoGrad. Wait, I don't know what's AutoGrad, but I'd be happy to take a look. Oh, okay. Right. The PyTorch thing, AutoGrad. I'm not entirely sure. I think there exist a few good PyTorch tutorials on YouTube. Jeremy Howard, I think he might have one. I think he has some tutorials on PyTorch. And otherwise, I think it's a great strategy. I think it's a great strategy to just look at the docs, to just look at the PyTorch docs and then paste things into, say, Claude or Gemini, and then just ask for explanations wherever you need that. I think that would be nice. Right. So I think that's it. Thank you all for attending this session. I hope I was worth your time. And yeah, thanks again. Have a good night. Yeah, bye. Yeah.